Hello, everyone, to another round of control system lectures. What did we do last time? We actually talked about, we started designing controllers, right? So the first methods we talked about were heuristic methods, right? So to recap, what are heuristic methods? Heuristics methods are purely based on experiments, right? So we don't have any mathematical description of our system. So, for example, we have an espresso machine in front of us, and we do an experiment, and based on that, we tune the controller. You can always kind of tune the controller by also not applying these methods, just trial and error, right? But in these cases, you don't know where to start from with your values. That's where the heuristic methods come into play to give you a rough estimation what could be a good value for your controller. Basically, initial values, starting points where you then start to fine tune. Basically, we covered those in probably not even more than 1 hour, right? And then we moved on to the so-called model-based methods. And model-based method, as the name says, are methods where you need a model, but not a physical model, but a mathematical model. So there's an intermediate step, right? You have your hardware and you build up a mathematical model of it. Well, actually, you don't even need your hardware, right? When you, for example, have an aircraft, you actually start the control design before you actually have the hardware ready. Because you have a lot of calculations from CFD, from FEM, you get mathematical models and you already can start designing controllers with these models, right? So it depends on the industry, basically, what the right direction is or what what's the way to go is. And the first methods in the model-based tools or methods, and we talked about our pole zero cancellation. So what are pole zero cancellation? From system dynamics, we know pole zero cancellation is simply when in the transfer function a pole cancels with a zero. So a zero in a numerator cancels a pole in a denominator, right? So that's a pole zero cancellation. But now we are doing this on purpose, right? Remember, poles define as a laggy behavior, right? PT2 systems, they are the poles introduce some lag, while we are free to choose in the controller. So we introduce zeros in our controller and take out the slow poles from our system in the closed loop, right? So this is the plain simple idea of pole zero cancellation. All the poles you don't like in your system, you start to cancel. Are you allowed to do this with every pole? No. If the pole is unstable, never cancel an unstable pole. I've shown you this example in MATLAB where we've seen, okay, if we do that, we are basically screwed because this cancellation in practice does not happen exactly, right? If we cancel an unstable pole, we might end up still with an unstable system, and this is not a good idea. Okay. Then we actually started to discuss the espresso machine, and we actually constructed us we constructed us a mathematical model of the espresso machine, and this is actually where we finished last week, and where I want to jump in today. So I'm going to switch over to the discussion from the last week. And actually, one of you actually figured out that the resulting system of the espresso machine is in the open loop, so without controller, is a PT3 system, right? We said we have 3 poles, right? And these poles are all in the left half plane, right? So if you draw the pole zero map one more time here, pole zero map of our espresso machine, of just the espresso machine, we have a pole at minus 0.2, we've got one at minus 8, and well, let's call that minus 2, minus 0.185, and the other one is probably here at minus 8.12. So this is the pole zero map of the espresso machine. Okay, so I know poles are kind of hard to interpret, so we said, okay, sometimes it's just easier to do a conversion into time constants, right? So you just need to take the negative inverse, and what you end up with is this pole, which is very close to the origin here, ends up with a time constant of 5.4 minutes. The second pole, -8, is a pole at 0.12 minutes. So, and the final one, which comes from the sensor, is about half a minute, right? So our system response, if we introduce a step into an espresso machine, is basically built up of these three eigenmotions, right? So these are all exponential functions you can think of when you do a step input, which you're adding up. And the thing is, this one has a time constant of 5.4 minutes. So this is actually the slowest one. This one is actually dominating our response because it takes so long. So if this guy here is at after 5.4 minutes, so 5.5 minutes, we have reached 63% of our response from this guy here, and all the others are actually basically over, right? Because this guy is 0.5, so it's a factor of 10 here. So this guy has already reached 100%, this guy too, when after 5 minutes. So this guy is really introducing the slow behavior. Why I'm discussing that in that detail is, remember we said with the controller we can take out a dynamics we don't like, and there we have to figure out what's the slowest dynamics in our system. And as in our example, these 5 minutes are so dominating, we're going to take out this one, right? Okay. Okay, so this was the discussion on the poles, and then we said, okay, we realized that our static gain of our transfer function is 420. This should not come of any surprise because this is what you should have computed in your first lab exercise, right? We put in the lab exercise, we put in 0.25 kilowatts, and we got out a temperature increase of 105 degrees. So if you divide that through, 105 over 0.25 is exactly 420. Okay, so what's next? So this is the model, right? So this is just the espresso machine, and now this is just the espresso machine. Everything what's green here, this is our model here, what we just derived. Let's write it down here. This is our G of S, which is a PT3 system, right? As in Simulink, this describes your espresso machine. So now we want to allow the user to specify a reference temperature. The user should not put in an heating, right? You should not need to put in 0.25 kilowatt or whatever to reach a certain temperature. What we want to do is we want to allow the user to say, okay, I want to have 90 degrees. I want to have 96 degrees of water temperature. Therefore, we have this measurement, right, of our water temperature because we have the thermometer here, and we are comparing that to our reference, and we're building the control error. And this guy goes into our controller, and the controller should generate our power for the heating element automatically, right? Some people would call it a smart system, but it's basically just a controlled espresso machine, right? So what the controller should do is find the temperature, find the power to the heating element that we actually reach our desired temperature. Okay, so what are our design constraints? Well, our design constraints, the whole thing should probably be faster than 5 minutes, right? Nobody wants to wait like 5 minutes in the morning that the espresso machine heats up, right? So this is probably too long. And we want to have it accurate, right? If I'm designing 96 degrees, I don't want to end up with 80 degrees. And we know a pure proportional controller is fast, so we can increase the speed of our espresso machine using a proportional controller. But as we figured in the lab exercise, we will never reach 96 degrees, so we will never be stationary accurate. If we want to stationary accurate, we need an integral part. As said last time, we are now fusing these two ideas. We use an integral component to get the stationary accuracy, and we use a proportional component to make our system faster. Okay, so we end up with a PI controller, proportional integral controller of the form. I mean, you can write the as just as a recap, you can write the PI controller in that form. Bring it on the same denominator, and you will see it has basically 1 0. We can freely choose and the gain. So either you choose the proportional gain and the integral gain, or you bring it on the same denominator, and it will show you basically you have 1 0 here, and you have this gain to choose, right? So 2 free parameters. Remember, a proportional controller only has 1 free parameter, just a P, just a gain. PI has 2. PID then has 3. And it doesn't matter if you choose the 3 gains of the 3 elements, or you bring it into a series structure and use the gain and 1 or 2 zeros. Most of the time, if you do it model-based, you will use the series form where you have the zeros there because you like to cancel. You like to cancel poles, so you need zeros in your controller, right? So we are free to choose the 0 and the controller gain, and this is what our task now is going to be. Okay, so let's take on the transfer function of our espresso machine one more time, right? I'm going to write it down. So G of S, it's just a pure transfer function of our espresso machine. So we said it's 420 over, and the time constants are those guys, right? 5.4 to 0.1, 0.5. Okay, let's write it down in a time constant form. 5.4 times S plus 1, 0.12 S plus 1, and we have 0.5 S plus 1, right? So that's the time constant form. So the problem is we have a polynomial of third order, right? We have a PT3 system. Actually, it should be written somewhere. Yeah, we have a PT3 system. And if we have a polynomial of a third order, it's always kind of complicated. This is why we're going to do an approximation, right? We're going to say, okay, this guy here is so fast, it actually, it doesn't matter, right? It's this eigenmotion is over so fast that it actually, we barely see it with the eye. And actually, this is not kind of something I said, you actually did that, because when you in the first lab exercise did the identification of the espresso machine, you said, looks like a PD1, let's identify the PD1. Okay, to be fair, I told you to identify the PT1, but actually this was a PT2 system. You just would have needed to zoom in very closely. You would have seen that the slope at the initial at t equals 0 is 0. However, when we zoom out, it looks like a PD1. Why? Because this guy, the 0.1 minutes is so fast, right? But that's not a big deal. If something looks like a PD1, we can say it's a PD1. We do an approximation, and the same thing we're going to do here to make our life a little bit easier. So we approximate this guy with 5.4 S plus 1, 0.5 S plus 1. Okay, what goes here? Question to you. Should be really straightforward. Think of when we did the conversions. This one is pretty easy. 420, yes, of course, right? We only cancelled out one, 420, obviously. We only cancelled out this guy. We stick to the time constant form, so nothing is changing, right? But just for practice, let's bring this guy also in the pole 0 form. this pole was s plus 0.85, and the second one was s plus 2. So what goes here? Yes, all answers are correct so far. Yes, 155.4. I've got 0.3, but I guess it doesn't matter at this point. So yeah, perfect. So remember, all transfer functions should have the same static gain. Otherwise, you're basically changing your static response. We only want to take out that eigendynamics, and I will show you in MATLAB how it looks like, and it basically looks the same, right? But if you change the static gain, then you're actually changing the gain of your system, and you should not do that, because then you will have a different controller gain, and you will have basically a wrong model you design a controller for, but you then, when you have designed your controller, you need to plug it into the actual model, into the hardware, which then looks different, and then you're screwed, right? Okay, so one point here, and this is really important, because it's I figured in the last semesters, this is always kind of a little bit of an, yeah, I don't know actually why it is a hassle, but it's actually plain simple, but students tend to make their life too complicated as it actually is. So, so we said we're going to design a PI controller, and remember, a PI controller has the form, for example, we have KPI times, it can have a time constant plus 1 over S, or it can have, it has the form, let's do this with a bar, times S plus mu, right? So these are the same. Obviously the gains you get out are changing, right? But these are both PI controllers. The one is in a time constant form, the first one, the other one is in the pose zero form, right? So, and now the question is, which one are we using? Well, which one are you going to use depends on your model you have, right? If I give you an espresso machine in the time constant form, I recommend you to use the controller also in the time constant form, because you can directly cancel. If I give it to you in the pose zero form, please use also a controller in the pose zero form, because then you don't need to do the calculations vice versa you don't need to change the form. Just you select the controller as you like, right? Because what's happened always, 50%, more than 50% in the exam is, I give you the model and say, okay, please design a PID controller. You are free to choose the PID controller, and the first thing what's happened is that students start to take the model and bring it into another form. This is unnecessary, because you're free to choose the controller. So if I would give you this model here, you choose this controller in the time constant form. If I give you this model, then choose the controller in the pose zero form, right? The result is going to be the same. Obviously, the controller looks a bit different, but you can, at the end, you can transform the controller between time constant form and pose zero form. It's going to be the same. So please don't change the model, because it actually brings you in a hassle, and the examples get more complicated than they should be, and actually you're losing time. So, okay, so I'm going to use the pose zero form, but for practice you can also do it with the time constant form. It doesn't matter, right? So as I'm using the pose zero form here, I'm going to say, okay, I'm using my controller also in the pose zero form, and my controller has some gain times it has a 0. We are free to choose S, right? And okay, what do we put in for mu for this free variable? Okay, our free variables are this guy and this guy, right? So we are free to choose those. Okay, and we said this guy here, this is the slow one, because it takes 5.4 minutes. Okay, so we take out this guy. So we say S plus 0.185 over S. If you want to do it in a time constant form, you write K times brackets 5.4 S plus 1 over S, right? It's really up to you. It doesn't matter. Okay, so Let's take this controller here and multiply it to our plant, because we know this is the open loop, right? We have our controller R and our system G, and we're going to do this first. Okay, it's just a simple multiplication, so we do G of S times R of S, which is equal KPI times S plus 0.85 over S times our system 155.4 over S plus 0.185 times S plus 2. Okay, and now we can actually cancel. Right, so we take out this from the equation here. Remember, you can immediately calculate the closed loop. You could immediately calculate the complementary sensitivity function. The problem here is that when you do the closed loop calculation, right? Remember the block diagrams, you always end up with double brackets, and then it's easier to do the cancellation before, right? So it saves you some hassle with all these double fractions, basically, not brackets, double fractions, right? Okay, so this is G times R. And now we can compute the complementary sensitivity. I'm going to write it one more time. Our complementary sensitivity of S is nothing but R times, okay, let's do it correct, R of S times G of S over 1 plus R of S times G of S. Remember, this is how the closed loop looks like. It's as we are feeding that signal back, we have a minus here to compute the control error. It ends up being plus here, and if you solve the block diagram, it's always going to look like this. Okay, and you see if you do the cancellation not before, because you have R times S appearing here twice, R times G appearing here twice, you would do the cancellation in here, and it's a little bit of a bigger hassle, right? Okay, so now let's plug in what we have. We got 155.3 kPi over, oh, I forgot the S. No, it's here. Okay, sorry. S times S plus 2 over 1 plus, and this whole thing again, 0.3 kPi over S times S plus 2. Right? And now if you multiply it out, this one goes here, it's 155.3 kPi over, bring that to the other side, multiply it by that, so it's S squared plus 2S, and then we have plus 155.3 kPi tilde. Okay, so this is now the closed loop from our reference temperature to our measured temperature Y. That's it. Okay, next thing, if you remember our lab exercise, most of you wrote to me, okay, we are not getting the temperature we actually require. We are not getting to 96 degrees. Yes, a proportional controller is never able to do that for a proportional system, but we've learned an integral controller is able to do that. So let's check what happens now for a step input, right? Because a step is kind of a user would apply, you would switch on your machine and you say 96 degrees, I want to have that. Okay, let's see. So we are basically computing the steady state gain, or the final value of the step response. You know, you do the Loomis function, you're basically saying you let S go to 0 because the S over S cancels, and what remains is 153 kPi tilde over 155 kPi. Oh, did I write? It was a 4 before, right? But yeah, it doesn't matter, I guess. And this is obviously always going to be 1, right? And this 1 actually means that in steady state, so if we just wait long enough, this guy here will always be transferred perfectly to this guy here. So we are receiving in steady state 100%, right? This means 100% from our input of the output. So we are achieving this temperature. This is what we see here. because we are now used to integrator. If you do the same thing only with a proportional controller, you will see that it's below 100%, below 1. Okay? So, where are we? Remember, we said we have two free parameters here. We have the zero. We used the zero already to take out the slow pole, the slow eigendynamics of our espresso machine. But we still have our KPI here. So the proportional integral, or the gain of the PI controller. And we are still free to choose this one. But here it does not matter for the accuracy. We already have the result that we achieve exactly the temperature we want. So we don't need to use that gain for the accuracy of our control system. So what we are using it for then? Well, we can use it to adapt the eigendynamics, right? Remember, when you remember the lab exercise, you turned the gain, it started oscillating, it started, if you turn it up, if you turn it down, it got slower, the oscillation decayed. So we can use now this free gain to set, for example, the desired damping, and we're gonna do this one. Okay, so let's write down our transfer function, our closed loop transfer function one more time. Okay, our T of S is nothing but 155.3 times this gain here over S squared plus 2S plus 155.3 kPi. So we are not changing the steady state accuracy if we change the gain, because it's always going to be 1, right? However, what we do change is we can change the dynamics of, or we can change the zeros, so to say, of the denominator polynomial, right? So if we change K, our eigenfrequency and our damping of this PT2 system is going to change, right? Because we changed that value in there. Okay, let's do it plain and simple, and let's compute the poles of that system. Our poles, we need to take the denominator and set this guy to 0, right? So these are the poles. And obviously, the poles are depending on where we select this guy. The poles are at a different location when we select KPI 100 than when we select it equal 1. Okay? So, what can we do with this one? Well, we know that this is a second order model, right? And a second order model generally written looks like the following: 2d omega 0 plus omega 0 squared, correct? This is when we introduced the PD2 system. So what do we have here? Well, we have one free parameter on the left-hand side, and we have two parameters which kind of depend on this guy on the right-hand side. What we basically can do is we can compare the coefficients, right? Okay, let's do this. So we're going to compare this guy with this guy, right? So what do we have? We have 2 is equal to d times omega, right? Okay, we can make that a little bit easier. We cancel this one. Okay, and we can compare this one. Okay, we have omega 0 squared is equal 155.3 kPi. So here you actually see, if you change your gain kPi, you change the frequency, right? So there's a direct connection here. Okay, still we now have two equations but three unknowns, right? This is our first equation, our second equation. So we don't know omega 0, we don't know d, and oh, sorry for that one. This should go, obviously. We don't know d, and we don't know our gain. So what happens now? Well, we have two equations and we have three unknowns, but one of these unknowns we are free to choose, right? We are free to choose the KPI, and we're not gonna use it arbitrarily. we're going to set the damping to a certain value we want to like to have, and then we compute the gain, right? So we just set one of these three values here. And I think a couple of slides before, we said we want to have a damping of 0.9. Okay, so let's try compute this KPI from this equation. You could now say, okay, let's do, you have omega 0 squared here, so you can write omega 0 squared from that equation is nothing but 1 over d squared, right? Okay, and now we take that equation and set it equal this one, right? So this one, omega 0 squared, must be omega equals 0 squared, obviously. So we can say 1 over d squared is nothing but 155.3 kpi bar. And now we can compute kpi, not bar, tilde, is 1 over d squared times 155.3. So what this equation tells us now, we have one equation, but two unknowns, but we can set one, right? Because we know we are free to choose our control gain, but we are not choosing that directly. We are setting one parameter in our system we want to like to have, and then compute our controller gain, okay? And we would like to have, we would like to have dB equals 0.9. So you plug that in here, and you end up with a control gain of 0.008. And this is now the controller you want to use, right? So obviously we cannot freely choose omega 0 at this point. We used our only left parameter in the controller to set the damping. Because we do that, we cannot set the frequency. So now you could say, what happens if I want to set the frequency? Yes, you can also say, I don't care about the damping, I set the frequency. Then the damping follows, right? Obviously, what you can do here is you can compute the frequency now. So if you take that and plug that back, or plug D back in here, you get a frequency of 1.1. 1 over a minute is that. But we are not able to freely choose omega 0 in that scenario. If you say, I want to choose my omega 0, it's a fair choice, you choose your omega 0, but then the damping follows. And why do you usually choose the damping? Well, you choose the damping because you know if the damping is positive, you for sure know the PD2 system is going to be stable. If you just say my frequency needs to be 1.1, you could end up with a system which is unstable, because you could have an unstable PD2 system with a frequency of 1.1, which is on the right half plane with a negative damping, right? To ensure stability, so that your system does not go to infinity, you usually choose the damping in that scenario. Okay, now we have everything, right? We have our we have set our two free parameters. So we actually could write the controller. So the controller now we want to apply to our espresso machine is nothing but 0.008 times what was the time constant, S plus 0.185. Right, so this is the final controller we want to use. Okay, that's it. That's the whole example, right? To be fair, the modeling part took much longer than actually control design part, and you should be more interested in the control design part. I only usually do the modeling part just as to take away that the lessons learned is that you have a sufficiently good model to do actually control design. But especially if you're an aircraft engineer, you get the aircraft models from a different department, right? But still, you need to know where it originates from and at least know to whom to talk to if something is wrong in the model, right? But yeah, the modeling is an integral part of control design. Okay, so last thing for the pole zero cancellation, before we move over to the next method, I want to show you a couple of plots of the espresso machine in MATLAB now. No worries, I'm not going to go into Simulink. Everything's prepared already. So what did we do? We designed a PI controller for the espresso machine. We canceled a pole, which we identified to be very slow. And then we used the final parameter to set the damping. And the results are an accelerated heating process, which is steady state accurate. So we are receiving our temperature. Okay, so let's take actually a look what we did when you draw the pole zero map. Remember, this is actually an error here. This must be PD2. Sorry for that. I'm going to correct that later on. Oh no, it's correct. It's fine. Don't worry. It's okay. No, it's okay because we actually simplified the espresso machine and kept the sensor. Remember, the espresso machine has a pole at minus 0.185 and the sensor has it at minus 2. So we kept those. This is the open loop. So this was our G of S. These are the espresso machine poles here. And then we introduced a controller, which is a PI controller. The PI controller has the form KPI times S plus mu over S. So this guy has a pole at 0. This is this one actually here. And we said this 0 is going to cancel that pole of the espresso machine. And you see the pole 0 cancellation here, right? This is basically a 0 over a pole, and whenever you see that, you basically know a pole has been cancelled by the 0, and in the Laplace domain, in the transfer function, they just disappear. This pole pair disappears, and this is important to know. Keep that in mind because later on we're gonna need poles and zeros to compute distances when we do root locus design. We do that in the afternoon. But when you see that cancellation, just ignore it because it's cancelled, right? It's 1. Right? So it does not influence your system anymore if you see this cancellation. Okay, so what we actually see here is the pure open loop, right? We have R multiplied by G. This is what this picture tells you. Not yet having the loop closed. It's really just your espresso machine and multiplied with the controller. Okay, and now what we did is we then closed the loop. So this guy here is basically taking our controller and closing the loop around. Right. This is now the closed loop. So what you see is these are the poles of the espresso machine only. So these are the minus 0.185 and the minus 2, right? And we introduced a pole by the controller and we took out the pole of the espresso machine and then we closed the loop and these are our new poles. This is our new system. Why there are again only 2 poles, although our controller has another pole? Well, it's again 2 poles because of this cancellation here, right? So we took this one out. So this is not appearing. If you close the loop, you move those poles up here in the closed loop. And this is what you see here. So this is your new closed loop system here. And if you look closely, it has a damping exactly of 0.9. 0.91 is this line here, and it's slightly above. Okay. And the eigenfrequency, these are these circles here. You should see it's roughly 1.1 here. There's this 1.1 circle going here. So the eigenfrequency of this guy is 1.1. Okay. So this would be the pole 0 interpretation of our system. Now let's look at the time responses, because ultimately we are human beings. We're likely to, or we like to think in time responses, right? Not always poles and zeros. So let's see what how the time response looks like. Okay, so the blue one is the original one, and to be fair, I scaled it with 420, right? I actually only want to show you the speed comparison. This one, obviously, if you put in a 1 kilowatt in your espresso machine, goes to 420, but this would not have been very nice to plot, so I just divided the output by 420 just to show you the speed increase what we did with our controller. And the orange one corresponds here to the closed loop system, and you see that we actually have an increased speed in the system, right? After 5 minutes, our system is actually at 100% heated up, while the original system actually needed 30 minutes. So it's definitely going to be a better argument to sell this espresso machine, which only needs 5 minutes, than the other one, which needs 30 minutes, right? So we did actually a good job, and we also know that we have steady state accuracy, so we are actually also achieving the right temperature. Okay, as promised, quick look into MATLAB. You can download this file as usual. You have everything there, right? It basically, recomputes all the plots. What I've shown you in the lecture. So you have the open loop poles, you have the reduced system, and so on. And this is actually the interesting one. This is what I promised you. This actually is our PT2 approximation of the system, right? The orange one, remember? I'm going to go back quickly. Here it is. We said, okay, this is our PD3 system, but this PD3 is roughly a PD2 system because this guy here is so fast. And we said, okay, I believe you, Professor Osman. And here is the comparison, right? The orange one is the PD2 system, and the blue one, you barely see it, is the PD3 system. So they are basically over each other. If you would have cancelled another pole, this would have not looked that nice, right? So here it's really okay to ignore that one because it's so fast compared to this one. Actually, also to this one. And it basically really kind of looks like, well, you could see a little bit of the laggy behavior. Yeah. Okay. And then it's the control design. You can go through it, and this is basically the the comparison of the espresso machine without the controller and with the controller, right? Last but not least, you can, last but not least, this plot is kind of important because this plot now shows you the following. We have a PD3, our system, our hardware is a PD3, but we said, it's approximately PD2 system. But now we're designing the controller for the PD2 system, right? And you take that controller designed for the PD2 system and plug it into your espresso machine, which is a PD3 system. So whenever you say, okay, I want to have a damping of 0.9 on my approximated system, in reality, when you take that controller and put it back to your original system, it will not achieve 0.9 because you achieve the 0.9 only for the approximation. So you need, as an engineer, you need to double check, right? Same thing with an aircraft. You say, okay, my aircraft is roughly a PD2 system, but I'm ignoring a lot of flexibilities of the wing, for example. What you're going to do is you design the controller for the simplified aircraft and then test it on the complex aircraft, on the higher order aircraft. That's okay because usually the design part is the hard part, while the plugging back in, the testing, the validation part is the easier part. You don't need to do so many computations. If you're fine with the result on the PD3 for the espresso machine, just go ahead. If you say, the approximation was too rough, then you need to kind of iterate. And this is actually what this plot shows you. The orange, these are the closed loop poles of our PD2 approximation. But our plant in reality, our espresso machine is PD3. And there you see, if you take that controller designed for the PD2 and use it, apply it on the PD3, you have a slight decrease of the damping. So although we said we want to have a damping of 0.9, in reality, if we take the controller back to this PT3 system, it has, I don't know, 0.85 or something, right? So this is, 84, right? So we have a little bit of a discrepancy, but this is important because we did the approximation. We always have to bear in mind, we do the approximation, it works okay. It helps us to do the design a little bit easier. So we have got a question in the chat. Is it possible to discuss sheets 2, 3A, 3C? Yeah, I'm going to do that in the last 5 minutes, or actually when the lecture is over. And then for those who actually were in the office hour yesterday, you can drop out, and for those who want some insight on that examples, you can stick around. But I'm just going to take like 5 minutes and I go through it quickly because actually we want to use the office hour for that. Okay, that's it. So really look into the MATLAB file if you're interested, or if you should be interested. You need to be interested in pole zero cancellation because it's definitely going to be part of the exam and what we do next. So it's crucial to understand that. Last slide for that lecture, I'm going to sum up the pole zero cancellation method. And to be fair, it's basically a sub-method, and you can often apply it, but you need to be careful, right? Okay, pole zero cancellation is a model-based design method. Please really ensure that it is a model-based. Without model, you cannot cancel anything because you need to know where the poles are, right? There are actually extensions which have been used for, I think, even the A350 aircraft, and also for space launchers, which basically not only cancel 1 or 2 poles, but cancel the whole dynamics of the system. But yeah, this would go too far in this lecture. It's primarily used for stable and lag processes, delayed process. So they need to be stable. So this is for sure, right? Never, really. If you do that in the lecture, it's in the exam, this example is going to be 0 points. Never cancel a pole on the right, in the right half plane, because it will fail in practice, right? So if you have a pole zero map which looks like this, you have a system which is clearly unstable, please don't put your 0 over here. It will not work. So never ever do this, please, right? Only cancel in the left half plane. So also, if they are oscillating and stable, you can cancel, right? So if they are here, you technically can put two zeros above it and you can cancel, because I told you never ever cancel on the right half plane. They are in the left half plane, you can cancel it. However, you will get maybe some problems, but this is actually what we're going to do next. So the method really works best if you have stable poles. You need to have stable poles, but they are non-oscillating, so they are on your real axis. So really, the sweet part of for the pole zero cancellation you want to look at is this here, right? The real axis in the left half plane. If you have a pole there, yeah, go ahead. Okay. Yeah, so we take the zeros of the controller to cancel, and the final parameter which is left is usually the gain, and you can use that gain to adapt the dynamics of your system. Okay, and that's basically it. And there we will actually have a couple of examples. If you also look into the exams, there are actually some examples in there where you need to cancel poles. So you can now actually try these examples. We actually can take a look quickly so you know what to do next week. No, I'm just kidding. Let's see, if you scroll down to the examples from last semester, you actually have here, if you go down, down, a little bit more down. Okay. It basically design a PI controller as a closed loop transfer function from the reference, blah blah blah, showing the same time constant as determined. So these examples are based on basically canceling your poles. So you can actually now start trying these examples if you like. Yeah, it's better not to wait until the end, because there are a lot of examples this semester I'm providing you. So it's going to be really a hassle if you wait until the end of the semester. So feel free, it's your choice, right? Okay. When did we actually start? 11:45. Okay, so half an hour left. I want to start a new chapter now because it actually turns over to a new method. And we're going to use this new method when the pole zero cancellation is, yeah, we will see it's not always working, right? We definitely already know it's not working on the right half plane. Whenever we have unstable dynamics, it's not going to work. So but still, we need to design a controller, because if we have an unstable aircraft or an unstable rocket, we want to have that system controlled and work, right? So what do we do then? We definitely not going to cancel the poles. So there needs to be something else. And we're going to introduce the next method, which is called root locus method. In Deutsch heißt Wurzelortskurvenverfahren. Wurzelortskurve, vielleicht haben Sie es schon gehört. And I'm going to motivate this root locus design by actually, sorry, by the fact that also for oscillating poles, the pole zero cancellation has a little bit of a drawback, right? And then we will take a look what we can do and what the root locus actually is. Okay, I'm going to turn over, and we're probably going to do this now for 20 minutes. In the last 5 minutes, I'm going to use for the examples here. Let's motivate this method. So it's another method, right, for a model-based design. We still need a model. Actually, all the methods I'm presenting you throughout the semester are actually model-based methods, right? So we are not doing any experimental-based methods anymore. We cannot cancel in the right half plane, because if we cancel unstable poles, it fails. In reality, you will not directly hit, right? You will not directly hit that pole in the right half plane. So if we have an unstable system, yeah, it's better to manipulate the pole location than to cancel it, right? So what you actually want to do is, let's say if you have your poles here, if you cancel it, it will go away, but it's still gonna be unstable because you don't hit it. So what you actually want to do, you want to move that pole somewhere to the left half plane, right? Because if your system G of S has a pole in the right half plane, and you are able to design a controller to move that pole, to drag it over to the left half plane, you're done. Because what you want is, you want to provide the user a closed loop system which is stable, right? So although the aircraft can be unstable, you want to, or a rocket's definitely always going to be unstable, right? So this is kind of a rocket which stands somewhere, it falls down, it's unstable. You want to provide the pilot of this rocket, I cheated, right? A rocket which is flyable, which is stable, right? Which does this. So as soon as your closed loop is stable, you're good. So what you need to do is, you need to drag this pole from the left half plane to the from the right half plane to the left half plane. So this is the idea, because canceling is not a good idea. So it's not a good idea to cancel it simply out of the equation. So much for the unstable pole. However, what happens is, why shouldn't we not now cancel this pole pair, right? So why is this? And here the situation is not so clear, and I want to try this example actually with you. Right? We're gonna now in the next few slides design a controller which is actually doing the following. We're gonna take a controller which cancels out these two poles, and we will see what's happening. Okay, so you know that famous system, we used it already quite a lot, I'd say. It's our PD2 system. Okay, let's write down what do we have here. We have a static gain of 0.25. We have an eigenfrequency of square root of 16, which is equal 4, and we have a damping of 1.6 by 2 over 4 is equal 0.2, right? So we definitely know this system kind of in the pole zero map looks like this. So it is very lightly damped. It has something like this, right? So it is oscillating. It is stable. It's in the left half plane, right? Because why do we know it's in the left half plane? Well, because our damping is positive. If the damping would be 0.2, it would be here, right? But we don't have that. Okay. And the design goal is we want to increase the damping to 0.9. So the damping of the new system should somewhere be here. This is where 0.9 is. And we want to have steady state accuracy. Okay. Steady state accuracy, we don't have it now because we have a gain of 0.25, means we only get 25%. Okay, so what approach are we going to use? Okay, you can say we have learned today that canceling poles is sometimes a good idea. So why not try, actually I can draw it above here, actually why not try canceling these two poles, right? So we're going to cancel this pole here with a PID controller, and we're going to introduce the PID controller has a pole at 0. We're going to introduce that. And we cannot, a PID controller is kind of non-causal, so we're going to use R of S. S, right? PI, the I of the integrator here. And then to cancel this guy here, we simply take this one and plug it in the numerator. So S squared plus 1.6 S plus 16. So this term of the controller cancels it. We still have a controller gain as a free parameter. And this PID controller is not causal, right? So we need to consider a parasitic delay and we're going to put it to a pole of minus 20 plus 1, right? So this is basically a PID T1 controller, right? So again, what did we do? We put the two zeros exactly above these two poles. We implement an integrator for steady state accuracy. As a PID controller is not causal, we need to have a parasitic delay, brings us another pole at minus 20. So we're going to take that in here. Put this one at minus 20. And we still have this free parameter here, right? And this free parameter, when we close the loop, will shift our poles somewhere we like, which is maybe going to be here, right? Hope this is clear. Okay, we will do the calculation on the next slide anyway. So again, we start out with multiplying our controller to our system. Okay, let's do it slowly. We have KPID times, we said, okay, in the numerator, we simply put the denominator of the system, 1.6S plus. I'm going to take a look at the question immediately after I've done this one. But I guess it's going to be on the 0.05S plus 1 times, and our system was 4 over S squared plus 1.6S plus 16. And now we actually can already cancel. right? So we cancel this guy here, we cancel this guy here. So the question is, how did you choose the pole, for the delay? I guess that means for the PID control, I guess. How did I choose the pole? I chose it far away from this guy here, right? So this pole here is about at 5, so I multiplied this by 4, right? So you should kind of put this pole far to the left of your system dynamics. It doesn't matter. You can set it to 0.01, 0.1 would probably also work. Why does it also work? Remember, when we talked about the espresso machine, we said, okay, if there's a fast pole in your system, it doesn't show up in your time response that much because it's much faster than the rest of the system. And this fast just means in the pole zero map, just put it far away from the others, right? So if this guy has an eigenfrequency of 4, you choose an eigenfrequency of 20, right? So a time constant of 0.05, right? You can put 0.01, you can make it faster. In practice, this is usually constrained by your microcontroller, how often per second this microcontroller works, right? If your microcontroller works with 20 Hertz, you're restricted by this 20 Hertz. But just make sure that it's much faster than the system. I guess 0.1 would probably also work, but the closer you move it to your system poles of your G of S, right, the more the influence you will see visually when you do a step response. So just to make sure to be far enough away. To be honest here, I just selected at -20 arbitrary. So please don't select it at -4 and -8. Something, a factor of 3 or 4 or 5 is usually good, right? And as we have this pole here at the frequency of 4, so this guy here is actually a little bit less than 4. Yeah, far away of your system dynamics is a good idea, right? I mean, if you're unsure, you can always do a step response in MATLAB, right? And see, does that pole influence my system or not? If it still looks the same, just take it, right? So it's really, yeah. Okay, where were we? Okay, so this is now R times G. We canceled already, and now we can compute the complementary sensitivity function. Okay, so we say T of S is nothing but R of S times G of S over 1 plus R of S times G of S, and now we need to put everything in here, which is 4 times K PID over. By the way, you can name that gain as you like, right? I'm just writing KPID that for you in the lecture, it's clear that it's the gain of the PID controller. So to kind of not get lost with the gain names. But if you say this is just K, I'm also fine with that, right? 0.05 S plus 1 over 1 plus whole thing again over S times 0.05 S plus 1. Okay, now we need to multiply that out. We end up with just this here, 4K PID over 0.05 S squared plus S plus 4K PID tilde. Right? Okay, this is 4. So you should see immediately that we are steady state accurate. If you let S go to 0, it's going to be 1, right? You have 4K PID over 4K PID, right? So I did the computation now basically in MATLAB. If you put in KPID equal 1.55, you end up with a damping of 0.9 and an eigenfrequency of 11. Again, same thing as before, right? You can do it on paper, you can use MATLAB. So as a practice, you can do it on paper. It's the same thing with the espresso machine. Do a comparing of the coefficients. and then you compute KPID, and you get or you compute KPID based on the damping of 0.9, because this was the design, right? We said we want to have a damping of 0.9. It's exactly the same thing. Okay. Okay, so far so good. What do we see here? We see here, red is not the best thing. We see here that this is a PD2 system, right? This is what we have expected. It's PD2, it's a little bit of oscillating. It's oscillating actually as we desire, because we are free to choose the damping. So, nothing to complain about at this point, because this is actually what we desired, right? Okay, and here comes the but. Here comes the but. Next thing we're going to do is we compute the disturbance sensitivity. We're going to take a look what happens if we inject a disturbance, like an unknown disturbance, like a wind in our car or in our aircraft or something like that, or a room temperature change for our espresso machine, something like that, right? Okay. Okay, this is already written here. Okay. So, let's compute the disturbance sensitivity. As a recap, just as a reminder for everyone, the disturbance sensitivity is important if we want to know how disturbance influence our output, right? Disturbance often enters at the plant input, right? So the plant, our aircraft is directly feeling the wind, for example. It's not, the wind does not come in to the controller first. So it's really acting on your physical system. And how now does this disturbance actually influence our output variable, right? So we're going to just compute this for our closed loop. Okay, and we know this guy is nothing but our system G times our sensitivity function S of S, which is nothing but G of S over 1 plus G of S times R of S, right? So you go directly, you go through G, you go 1 plus the circle, you go R times G. Okay. Please, you can do this at home. For practice, I'm going to give you the result because it's a little bit nasty. What the output is 4 times S times 0.05 S plus 1, S squared plus 1 point S plus 16 times, and now 0.05 S squared plus S plus 4K PID tilde. So, what do we actually have here? We have a D2T4 system, right? Okay, this was just for fun. This D2T4 system. The more problem is, what I want to actually point out is that now suddenly our actually cancelled pole pair shows up again in this transfer behavior, right? You see, you have actually the pole pair we have here, right? The nice one, the stabilized one, where we increase the damping, it's here. But you also have the pole pair, which was the original one, right? So this slowly damped guy, which we actually wanted to get rid of. And what that means is that if you can, and this is always true, if you cancel something with your controller, you only cancel it from the complementary sensitivity function, but not from the disturbance channel, from the disturbance sensitivity. Meaning that the disturbance can always excite this lowly damped behavior, and this is obviously not good. So the point is, you still can cancel it, but you need to be aware that if you have disturbances, they're going to excite that thing what you damped, right? And this is what we have just seen here with our simple calculations. So the weakly damped pole pair still appears here in the disturbance sensitivity, and thus this guy here, this wind, this side wind, can excite this lowly damped motion. Okay, you can read this. What stands in here is simply this is also true if you cancel an aperiodic pole, right? So if you have a temperature change in the espresso machine now for our controller we just designed, it's also gonna, you will see that aperiodic motion also in this disturbance sensitivity there. However, as it is aperiodic, it's probably not so problematic, right? Usually something which is oscillate in your loop is harder to cope with. Think of a car. You do a design and the driver can inject a very nice signal and it's perfect. But as soon as the wind comes, the car is driving left and right like wild. So this is definitely not going to be a good behavior. So we need to think of something else. Okay. Bottom line here is whenever you cancel something, it still can be excited by your disturbances. This is always going to be true, right? So be careful. And these are the results now if you do the simulation. Okay, let me switch to my laser pointer. This is the open loop, right? This is just our system itself. This was this second order system. G of S being, don't remember actually, 4 over S squared plus 1.6 S plus 16. This is how the step response for that system looks like. If you do the control design via canceling the poles, this is your new answer, right? And if you compare that, so this is your basically the simulation of T of S, right? So reference signal to your output. And you definitely could say, okay, this is kind of an improvement, right? This guy, the blue one here, is exactly the same as this one. We have achieved steady state accuracy, it goes to 1, and we have damped the system, and it's much faster. So where's the point to complain about? Well, the point is here, right? If you look at the simulation of the disturbance sensitivity, so meaning that how does a disturbance influence your output? You have some oscillations in there, right? And often you don't want to have that oscillations, and often such oscillation in your system are problematic. And this is why canceling a pole pair which is oscillating is sometimes not always a good. I'm not saying you should not do it. When should you do it? When you are sure you don't have any disturbances. Okay, when you know you don't have any disturbances or your disturbances are pretty small in practice, you could still cancel because the reference to output behavior looks okay, right? There's nothing to complain about. However, if you have disturbances, be careful. So as soon as you have a system which is working in the outside, like a car, a bike, a motorbike, an aircraft, a ship, they will be prone to disturbances you cannot know, like wind, waves changes, whatever. However, when you have a robot arm, for example, which is built in your lab, probably there are no disturbances, and there an inversion could or a cancellation of this pose could work. So it's really depending on the problem, right? Okay. Bottom line for us, I know this was now a lot of practical insight. Bottom line for you as a student, before you go out and work in controls, is we need to have an additional method where we don't cancel this lowly damped poles, but we shift it, right? We shift it actively to a position we like instead of cancel it simply out and introduce new poles. Okay. So what actually happens in the pole zero map if we don't cancel them, right? So we say, okay, the first approach was we cancel them, we introduce new poles, and we shift them those to here. What happens now if we don't cancel these poles, right? So what if we don't cancel them and we introduce a PID controller? What happens then to these poles which were there before? Well, the answer is actually simple. By introducing a controller, we also gonna shift those poles, right? If you don't use the controller to cancel the poles, you're gonna shift them somewhere else with the controller. The question now is, how does this work? Is there a strategy? The good news is yes. And why is it there? And this is what we're going to answer in the second part of the lecture. For now, you should go away with the fact that you understand what pole zero cancellation is. You take out poles which you don't like, but you always need to be aware of the fact if you take them out, they can still be present in the disturbance channel. And this is actually another reason why you should never cancel unstable poles. Because if you cancel an unstable pole, you only cancel it from the reference in the complementary sensitivity, from the reference to your output. But it's still going to be there from your disturbance to the output. And as soon as this unstable pole is there, your system is going to be unstable, right? So another point why canceling in the right half plane is not allowed. Yeah, let's state it that way. Okay, for those of you who like to take a break now, you can actually take the time, and I'll see you at 3:15. And for the rest, I'm going to take a close look into these three examples. So start out with, we've got transfer function, right? This is, I guess, what you're supposed to mean. We've got the first class of you need to compute the steady state value. This is kind of clear. So now example 2. Sketch out the output signal y of t of the system to a ramp input y of t. Okay, so what you see here, let's do the following. Let me switch this. Okay, so let's take black. Okay, what do we have here? We have a DT1 system, right? So we have a differentiator which is lagged. If you write the differential equation, it would look like this: 1 over, this does not work here. (0.1 y dot plus y is equal 4 times u dot of t. So your input is a ramp. So u is a ramp which looks like 0.1 t. So this ramp is differentiated. So a differentiation of this guy is 0.1, right? After time. Multiplied by 5 is 0.5. This is what you have here. So this is constant. This needs to go to 0.5 in steady state. And now you have a lag of, it's a DT1, so you don't have the answer immediately. You have a lag of a time constant of 0.1 seconds, so it needs to go something like this. And you're achieving 0.1 times 63% after exactly 0.1, and you are at 95% after 0.3. That's basically it. So what do we have here? This is simply a PT1 system, right? So this is PT1. If you write the differential equation, it should be clear. And the time constant is 1 over 12. So it's about roughly 0.089, something like that. And you have a ramp input of 2t. The gain here, your steady state gain, is 1. Okay, so if your input is 2t and you multiply this in steady state with a gain of 1, it also should increase with an Steigung of 2. I don't get the word at the moment. Okay. However, it's delayed, right? It's again a T1 system, so it needs to have some delay here, lag here, right? And if you look at the integrating first order system, you see that this is about 0.09 seconds here. Okay. I guess the others are kind of similar. Well, this one probably you have an integrating system now. You have an impulse response. Well, an impulse input looks like this. If you integrate that, it must be somehow look like this, because this is what system do we have here? It's an IT1, right? So it's again must look like something like this. Well, consider this 3. That's basically all you need to do here. Okay, this now is an IT2 system, so it's a little bit oscillating. You compute the damping, you compute the eigenfrequency, and thereby you know how the thing is oscillates. You can compute the overshoot from that, and the time period from the first to the second peak. Hope that's clear. Okay, so what else do we have? 3A and 3C. Okay, let's go over these ones. The graph below depicts a system response to a ramp input. Provide the transfer function. Okay, so what do we see? We know that our input is a ramp and has a Steigung of 2, right? So this is T and this is U. Okay, what do we get out in steady state? We get out a value of, this must be 1. This is 1, so this has is 1, right? So our gain of that transfer function must be 0.5, because we need to go from 2 to 1. If I'm not mistaken, it looks like 1, yes. It's going to be 0.5. So, and do we have the system response immediately? No, there's again some lag, but it's not oscillating. So what do we have? The only thing we can have is a PT1 system. And again, we get the time constant by the tangent here. Should be roughly about, don't want to say it here because my tangent here with the board is pretty bad. So you know how to draw a tangent on that line. Okay, that's 3A, and we got 3C. Okay, so what do we have here? An impulse, right? So our input looks like this, and it's 0.5. Okay, so this input gets 0 for t going to infinity, right? Okay, this output, y of t, is not 0, right? So it cannot be proportional, because if I multiply 0 by something constant, it's going to be 0. To get a 0 to a constant value, I need to integrate over this guy. So it needs to have an integral element here. So our g of s needs to be 1 over s something. Okay, so we have an input amplitude of 0.5. This goes to 0.25. So the gain is 0.5, right? Because 0.5 times 0.5 is 0.25. Okay, so everything which is in the numerator here kind of defines the eigenbehavior, right? And we definitely see this is oscillating. Okay, so it needs to be, it cannot be a PD2 element, but a PD1 element. It needs to be PD2. So we have 2. Now let's write it differently. Where's my 1 over omega 0 squared s squared plus 2d over omega 0 s plus 1. Okay, so what do we have? We have an integrating second order system. And remember, why can you look at a PD1 system, a PD2 system to get out all the information you need? Well, an IT1 system is nothing but a IT2 system is nothing but a PT2 system multiplied by an I system, right? This is the integrator. This here is the PD2. You end up with an integral second order system. Okay, so what are we missing? The eigenfrequency and the damping. Well, the damping is the easiest way. You calculate the overshoot here. 0.5 goes to 0.375, so the overshoot is 50%. You look in this on the slides where you have this overshoot over damping, and you get out the damping and the eigenfrequency you get from compute the time period TP from one peak to the other. From there you can compute the damped eigenfrequency, and from there you compute the undamped eigenfrequency, almost zero, everything in the script. Okay, so there's something in the chat. Damping would also be nice. Yes, I think I've got that covered. So you get the damping over the overshoot, or you get it via the logarithmic decrement. There are actually two possibilities. I'm going to show you quickly if I find it, and then we are done for this first part. So if you know the overshoot, you go into that one, 50%, go here, go down, it's about 0.25 or something, 50, yeah, something like that. Or you compute it with the logarithmic decrement, because you know A1 and A2, you get to the first two peaks, you compute mu over the natural logarithm, you plug it back in here, you get the damping. And here you see you get the frequency omega e over this time period TP, and then you calculate it with the damping, and omega e you get omega 0. That's basically it. I hope it was not too fast, but I needed to stick with within the minutes. You can always run it slower, I guess. Okay, I'll talk to you in 2 hours. Have a good lunch, and yeah, take care. Talk later.